Starting out here in section 2.3 and 2.4, now that we have left the whole concept of graphing lines and all about graphing lines, remember the whole goal is being able just to find the slope. And then once we get the slope, the kind of the rise over the run in the graph, then if we take another point, we can easily graph it. Or if you think about another concept is we learned about parallel lines, or two lines that have the same slope. Perpendicular lines are two lines that have slopes that are opposite reciprocal. Vertical lines are equations that have only the x variable in it, and they always have undefined slope. Horizontal lines are equations that only have the y variable in it, and they always have a slope of 0. Okay, so let's go into the world. Let's kind of expand a little bit past lines. Let's go to some other types of graph. And what we're going to call these graphs are things called functions. So here, looking at this first bullet, is if we take all the graphs that we know in the world, the circles, parabolas, V's, curves, slight curves. If we take all these other graphs out there, besides not lines, we can include lines as well, but just let's broaden our horizon just a little bit. We have a very specific group out there, and we're going to call these the functions, okay? It's a very special group called the functions. And in order for an equation to actually be a function, or in order for the graph of that equation to be a function, we have some key points here. In order for a graph or an equation to meet the requirements of being a function, the graph has to pass the vertical line test, which just means that, like let's take a parabola for instance. I just take any generic parabola right there, okay? If I want to come across this and draw a vertical line anywhere, I want to be able to draw it anywhere on that graph. As long as that vertical line only touches the graph one time, then we know for a fact that we have a function. And so what really is happening, if you want to look at it in terms of the equation, is that whenever I plug in a single x value, what's going to come out is a single y value. So it's like for every input, there's only one output. For everything I plug into the equation, only one thing is coming right back out. So by the time you combine these two concepts, the concept of, well, the graph itself has to pass the vertical line test, or if I look at the equation, if I plug one value in for the x, then that means only one thing is coming back out from the y. Then we put these two together, and that's what makes a function. Okay, so let's go on to the next point. Once you have checked for the vertical line test, if you want to check for the one thing in, one thing out thing, then when you once a graph or equation is known then to be a function, we have a special notation for it. We almost want to be able to declare it this function. It's got this title, now let's declare it. Let's make it stand out a little bit more. And how you do that is you look at your equation, we make sure it's in slope-intercept form, so it's solved for y, just y equals mx plus b, we make sure it's like that. And once it's in that form, what we do is we take away the y and we introduce this new thing called function notation. We can either replace the y with f of x, h of x, or g of x. And notice how I say it. It's f of x. This is a function of the x variable. This is a function of the x variable. And the f, h, and g out front are just a way to name them. So that way, if let's say we had 14 possible functions or equations written on the board, and we want to be able to go through and narrow them down, we can just title them each differently. A of x, b of x, c of x, all the way down the line. Okay, so just to recap about this in general, if I had an equation like y equals 2x plus 3, and if I know it's a function, then what I can do is take away the y and just name it. Let's say we want this one to be b. Now, whatever is going to be in this parentheses is always the variable that's on the right side of the equal sign. So in case the variable on the right is an x, then it's a b. So b is a function of x, and it equals specifically 2x plus 3. If you had an equation, let's say y is equal to 2a squared plus 3a minus 1, then take away the y, replace it with a function notation. Let's call this one maybe h. So h, and the variable on the right this time is a. So h is a function of a, and it specifically equals 2a squared plus 3a minus 1. Okay? And so when you look at an equation and you see that the equation is written in function notation, right away, if you ever had to graph it, you would know it for sure. 100% passes the vertical line test. Okay. Here in example 1, we're basically going to go back to our roots. We want to find what y is going to equal specifically when x equals negative 3. So find our y value when we know that x is negative 3. Well, just like that, we know what x needs to be, so let's just plug it in. So y is going to be 5 times negative 3 plus 6. And finishing that out then, so negative 15 plus 6, so y is equal to negative 9. So when x is negative 3, y is negative 9. If I wanted to come back and graph this equation right here, I know for a fact it goes to the point negative 3, negative 9. Okay, now that's a linear equation, and I know all lines, if I wanted to graph it, say up there at 6, has a slope of 5, just doing something like this, I know for a fact it passes the vertical line test. So this line right here is a function. Let's come down here. This says find f of negative 3 when f of x is equal to 5x plus 6. So this is saying when this function is 5x plus 6, I need to find f of negative 3. Okay, the way we word example 2 is exactly what example 1 had us do. It's just how to word example 1 using function notation. So if I took everything in example 1 and I said, just describe all that but use the words functions instead, this is where example 2 is coming from. So instead of find y when x equals negative 3, that's all of that sentence right here where it says find y when x equals negative 3. All of that can be shortened to that thing right there. It's a much shorter notation. That's why it was kind of developed. It was just helped to kind of like a shorthand in math. Okay, so f of negative 3, see how instead of saying f of x, we replace the x with a negative 3? That tells you what to do. If I replace the x in the parentheses with negative 3, then replace the x on the right side also with negative 3. It's as simple as that. So f of negative 3 is equal to negative 15 plus 6, or f of negative 3 is equal to negative 9. So again, whatever's in that parentheses is always an x value. What comes out is always a y value, and it gives you the exact same coordinate, negative 3, negative 9. Okay? So always the number, whatever's sitting in this parentheses, is always going to be what's plugged in for your variable on the right side. All right, let's go to the example 3. Just get just a little bit more practice on using function notation. So I have a function g of x this time. So g is a function of x, and it equals 3x squared minus 6x minus 3. So if we want to find g of 2, remember that anything that's in there is an x value, or it goes in for the variable on the right. So it'll be 3 times 2 squared minus 6 times 2 minus 3. So it equals 3 times 4, making sure I do my order of operations. Got to do that exponent first. So 12 minus 3 is equal to a negative 3. So all in all, we know that g of 2 equals negative 3. Or if I eventually had to graph this, I would write the coordinate 2, negative 3. There's the answer for that one. Okay, let's go on to the next one. Okay, remember, whatever's in this parentheses is what we're plugging in for the variable on the right. Up here in the first part, we plugged 2 in because 2 is in this parentheses. Well, in this case, an a is in the parentheses, so all we're going to do, again, is for wherever I see the variable on that right, I'm just plugging in whatever's in that parentheses. Well, in this case, since it's not a number, I really can't clean it up any more than this. So g of a is equal to 3a squared minus 6a minus 3. But we're just getting practice on how to word these. That's all we're doing. Okay, so let's go one step further. How about we're going to plug in a plus 1 this time? Okay, so our main equation tells us take 3. Whatever's in that parentheses, I have to square it. Then I have to multiply it by 6. And then I do minus 3. That's exactly what that equation is telling us to do with whatever's sitting in that parentheses. Well, right here, my base that I'm squaring has more than one term. The only way to square more than one term is to multiply it out side by side. So don't get caught in that trap and say, oh, it's just a squared plus 1 squared. Not so much. We've got to multiply that base out. And over here on this next parenthesis, just making sure I distribute everything correctly. So this will be 3 times, let's multiply this out. A times a is a squared. The outside will give us an a. The inside will give us an a. So a total of 2a. And 1 times 1 is 1. Minus 6a minus 9. All right, so kind of working on this some more. We'll get 3a squared plus 6a plus 3 minus 6a minus 9. So positive 6a and negative 6a, and we're ready for our answer. So g, the function g, when a plus 1 is plugged in, it's going to equal 3a squared minus 9. Okay, so as a rule of thumb, let's look at this. Whenever I'm plugging in an actual number, a number comes out. When I plug in a variable or any kind of other variable, like here's an a, look, everything in terms, my answer is going to be terms of the variable a. Or it's not going to give an exact number like 3 or negative 3 did up in the first part. Okay, so you're plugging in a number, expect a number to come back out. If you're plugging in something with a variable, expect something with a variable to be your answer. All right. And again, like there's a little note. Whatever's in the parentheses is what you replace the variable in the equation with. So the variable, let's say if I want to put this on the right in the equation with. Okay, so if I replace the x on the right with 2, I replaced it with a, then I replaced it with a plus 1. All right, so let's go on to example 4.